Okay, so welcome everyone for the sixth lecture. Maybe before we begin, like a couple of usual administrative announcements. Um, so we had a gather town last Friday, and even though there were not a lot of people as I expected, there were a decent amount of people, and I hope you found it useful, like to network with other students in the class. And if you liked it, like let me know through the anonymous Google form or by email. And if more people are interested, like probably we could do one more gather town, like towards the middle of the course or in the end of the course. Okay, so and another like important announcement is a lot of you are sending private messages in Piazza to the TAs for the doubts in the assignment. So please use the assignment tag and make your questions public so that other students who also have those questions will get their questions answered. Otherwise, what will happen is like TAs has to answer the same doubt for 20 different students, like again and again, like in these private chats. So I have asked the TAs to make these chats by default public, like if you send it, even if you send it as a private chat, but let's just make it as a policy that like if you're going to ask any questions regarding the assignments, that has to be like visible to everyone in the class. Okay. Okay, so now let's start. So we will start with a quick recap of the previous lecture. Okay. So in the previous lecture, we looked at gradient descent, like a way to minimize some objective functions where like you cannot come up with a closed form solution, right? Like, so the basic idea in gradient descent is like you start with some random initialization and like you take the gradient in that particular position. It is going to tell you like the negative of the gradient is going to tell you the steepest descent that you could take. And like you have an extra learning rate, which decides how much you are like how far is your step. So for every for every parameter w, you update it as w is equal to w minus some learning rate times the gradient, right? And like we discussed about like what are the issues with the learning rate and like how to do full gradient descent. And we also discussed about how to do like stochastic gradient descent. And we also discussed about the problem of like using gradient descent while like when you have like nonlinear functions that you want to minimize, right? So the problem with nonlinear functions is it's going to get stuck at a local minima. And stochastic gradient descent, on the other hand, has more chance of finding the global minima simply because it's a noisy approximation for the true gradient descent. Okay, so then we started looking at L2 regularization, which is also known as rich regularization or rich regression or weight decay. And we derived the closed form solution for L2 regularization. And we found that what L2 regularization is trying to do is to add this lambda times I, the identity matrix, to the X transpose X. So what does this mean? This means that you are adding a small positive value to the diagonal of X transpose X. So even if X transpose X is not full rank, so this addition of small positive value throughout the diagonal is going to make it non-singular, and hence like you could do the inversion, right? Like so this is one way in which regularization helps, but we also know that the other way in which regularization helps is by like acting as like by helping us to avoid overfitting. Okay, so this is where we stopped, and I think we still have like some part left from the previous lecture, so we will finish that before moving to today's lecture. Okay, so now let's look at, so far like we have been looking at the optimization problem for for example, in this case, we are in the linear regression setting where you're interested in minimizing y minus xw transpose y minus xw, right? Like, so you are interested in finding the w which minimizes this squared error, right? Now what L2 regularization is trying to do is to add a specific constraint to this optimization problem and make it a constrained optimization problem. So the L2 regularization says that you want to not just, you don't want to just reduce this least square, but you also want to make sure that the magnitude of the W is smaller, right? So now there is another way to like formulate this L2 regularization, which is in the form of constraint optimization. So the constraint optimization here is as follows. So we are interested in minimizing this least square error subject to W transpose W less than or equal to eta. Okay, so now what does this mean? Like, this means that you want the W square to be less than or equal to eta. So this is basically the equation of circle in 2D with radius eta over the origin, right, in 2D, and you can extend it to ND, right? So now we can easily show that this eta is actually proportional, inversely proportional to the lambda parameter that we have in the ridge regression. So if you look at this total error function, which is the least square error plus lambda times the L2 regularization, right? So now this lambda is inversely proportional to eta, which means that if you have a bigger lambda, then like you give more importance to the L2 regularization, which means the weights are going to be much smaller. So the eta is going to be much smaller. On the other hand, if you have smaller lambda, it means less regularization. So you have a bigger circle to cover, which means eta is larger. Okay, so now here is an illustration of how L2 regularization will work, right? Like, so in this case, you see that the center of this circle is the W solution that you would obtain if you're just doing plain linear regression, like no regularization. Okay. On the other hand, like if you add an L2 regularization, now in this case, like there is some eta, okay, which is decided based on the lambda, right? So now the constraint basically says that you can only find a solution within this circle, right? Like, so you will, so L2 regularization is forcing you to find the parameters which has lower magnitude, and that the maximum limit is decided by this circle. And the solution is basically a point where this circle intersects with some contour map of this loss function, right? Like, so now this dot here is the best solution that you could achieve by using L2 regularization. On the other hand, if you were not using the regularization, then you would have found this point, right? Like, so now this point might be an overfitting solution if you have chances for overfitting. Okay, so now this is like the geometric interpretation of what L2 regularization is doing. So as we increase the value of lambda, this circle is going to get smaller and smaller, and hence you're going to get weights which are smaller and smaller. Okay, so maybe before we move on, like, is there any questions about L2 regularization? Either post your questions or raise hand. You know what? Okay, just give me 1 second. Okay, Okay. Uh, any questions, comments? Okay, so then maybe let's continue. Okay, so we have seen L2 regularization so far, but there is also L1 regularization that one could do. So in the case of L1 regularization, my regularization term is simply mod W. Okay, so instead of, like, remember that in the case of L2 regularization, it was W transpose W, W square, right? Like in this case, it is just absolute value of W. So now my objective function becomes minimize Y minus XW transpose Y minus XW, okay, plus lambda times W, okay? So now in this case, for L1 regularization, there is no closed form solution. Okay. Also, this function is not differentiable at W is equal to 0. So this function, like just like how we call L2 regularization as ridge, like, so this is also known as lasso. So we cannot do closed form solution here, but you could do gradient descent. It is just that you need to be careful because like while you're computing the gradients, because like it's not differentiable at W is equal to 0. But in practice, like W is equal to 0 is not going to happen. So you just need to be very careful. Like we just need to be careful with the implementation. Now, what is the corresponding constraint optimization problem? So in this case, it's going to be very similar. So minimize Y minus XW transpose Y minus XW, right? Subject to the absolute value of W is less than or equal to eta. Okay. So where again, eta is proportional to 1 by lambda, depending on, like, if you increase the lambda, eta is going to be smaller. Now this is an equation for a simplex. So this is how this constraint would look like. So in this case, in 2D, it looks like this, and in 3D, 4D, it's going to become a simplex. Like in n dimensions and n dimensional, n minus 1, like it's a simplex with n minus 1 values. So here you can see that this dot in the center of this contour map is what the solution of regular linear regression is. And when you use a lasso regularization, like so you, like, basically, like, you will find the intersection of the possible regions that lasso allows versus, like, with the solution that you want to achieve. And in the case of L1 regularization, there's a more chance that as you decrease the eta, more of WIs will go to 0. So in this case, sorry, as we increase, just give me 1 second. Okay, sorry for that. As we increase the value of lambda, eta decreases, and hence more WI will go to 0. Okay. So sorry, just give me 1 second. Okay, that's not COVID. Okay, so in some sense, L1 regularization does feature selection. Why? Because it sets most of the features to zero as you increase the strength of L1. In some sense, it sets the weights of irrelevant features to zero. Like other way to look at this is like L1 regularization prefers sparse models. So there are certain benefits in like having a model sparse. Like maybe we could discuss about this in one of the later lectures. But for now, like, are there any questions on L1 or L2 regularization? So I think in your assignment, like you are expected to use L2 regularization and do feature selection using L2 regularization. But normally you would use L1 regularization to as a way to do feature selection simply because it sets a lot of like irrelevant features to zero. Okay, so I think concludes our discussion on regularization. So any questions before we start the new topic? Okay, so what is the advantage of using L2 regularization over L1 regularization? Well, there is no, okay, I'm not sure like if there is a clear suggestion on which regularization to use. So as I said, like L1 like is going to reduce the magnitude, but is not going to set it to zero, right? Like, so on the other hand, sorry, L2. On the other hand, L1 is going to set a lot of weights to zero. So depending on whether you want a sparse model or not, like you would go for L1 or L2. But L2 regularization is probably the most common regularization that you would see. And in some sense, this is also a hyperparameter. So you could try both L1 and L2 and do model selection. Okay, so L1 produces sparse W matrices, but I don't get why it likes sparse models. Oh, okay. So by saying, okay, probably like I said, prefer sparse models just because it produces sparse W matrices. So when your W matrix is sparse, then like your model, in some sense, one way to look at this is like, let's say I have 1,000 features and L1 sets 20% of them to zero. Then I could save a lot of computation because like I don't need to use these 20 features. So that's one way to look at like the sparsity. Okay, so now let's start with today's lecture, which is about empirical risk minimization. Okay, so maybe before we begin, I just want to like give a quick uh, tip for today's lecture. So today's lecture might be a bit more mathematical than like the lectures that we have seen, or probably the lectures that we will see in the future. But we are going to discuss some of the central concepts in machine learning, including bias and variance. So my general suggestion or advice for this lecture is it's okay if you don't get the math in the first attempt. So please don't stop following the lecture. So what is more important than the math is the intuitions, or the intuitions. So whenever I do some complex math, like I would also translate it into intuitions by the end of that particular section. So what is more important is probably the intuitions. Like, so you could always go back and like redo these math by yourself. So if you think this is too mathematical, like don't worry, like just follow the intuitions. Okay, so now we are going to look at like the regular regression setting again. Okay, so let us consider x to be some random variable which has, let's say x is p-dimensional. Okay, and y, the target, is just a single real value. Okay, and we are always interested in finding a function which maps x to y, right? So let's call that function as h. Okay, so h is a function from x to y, and in some sense h is also known as the hypothesis. Okay, so in general, there are like infinitely many possible hypotheses, and our goal is to find that one right hypothesis, which will have, like, let's say, zero generalization error, right? Like, so even though we have discussed informally in the previous lectures that zero generalization error is not possible because there is always some irreducible error in any task, right? Like, so we are going to formalize these intuitions today by using some theory. Okay, so, and also remember that like we discussed about two classes of algorithms. The one was nearest neighbors, but then like we found that nearest neighbors is a universal function approximator, but it doesn't work when you're in high dimensions, right? Like, so that's why we resort to model-based algorithms like linear regression, right? So in the case of model-based algorithms, we typically define some model f. Okay, so in the case of linear regression, the model is just w0 plus w1x, assuming x is a scalar, right? Or if x is a vector, you have f is equal to w transpose x, right? So this model, this function f is parameterized by some w. Okay, now for every possible w, let's take some w, random w configuration, w plus. Okay, now this function which uses this w plus to make prediction, right? So now this is one hypothesis. Okay, so basically for every possible configuration of w, you have an hypothesis. And again, the problem is same. Like, so we are interested in finding the right hypothesis which will have zero generalization error, right? Now finding the right, so far we have been looking at this minimization problem, which is basically you set up an objective function and you find the w which minimizes this objective function, right? So finding the right set of parameters for the model, right? So this is actually equivalent to finding the right hypothesis from the given set of hypotheses supported by f. So remember that f is a parameterization, right? Like, so for example, if you take linear regression cannot capture all possible hypotheses. It can only capture hypotheses which are linear in nature, right? So basically there is a restricted set of hypotheses that every function can support, and the minimization process that we are doing is interested in finding the right hypothesis provided within this restricted set. Okay, and we often do that by considering the expected prediction error, right? So let's define the expected prediction error for a hypothesis H, which is basically expected loss in using the hypothesis. Okay, and we have already seen this in the previous lecture. This is basically integral L of y comma h of x, probability of x comma y, dx dy, right? So now this particular expected prediction error, right? So we are going to call this as the risk associated with some hypothesis H. Okay, this is the risk associated with the hypothesis H. Let's just call this as R of H. Okay, so what have I done so far? Like, so basically there are a bunch of hypotheses that we are considering, and we want to pick the hypothesis which has minimum expected prediction error, right? So now this expected prediction error is the risk associated with this H. So we are interested in finding a minimum risk hypothesis. So the goal is to find a hypothesis H, let's say H star, okay, among the class of functions for which the risk R of H is minimal. Okay, so another way to look at this optimization function, like optimization process that we have been doing in the last few lectures, is like H star is equal to R min R of H, where H belongs to some hypothesis class. Okay, so in general, this RH cannot be computed. Why? So I think for now, by now we have seen this several times. So why is it not possible to compute this RH? Any answers? Raise hand, chat. Okay, Bruno.
We don't have the true function?
Yeah, so we don't have access to the true probability distribution, right? So that is why we cannot compute this risk, right? So we cannot compute this risk, but we are interested in minimizing this risk. So how can we do that, right? Like, so now the standard approximation that we are going to take, which we have already taken in the previous lectures, like we are just formalizing here, is instead of using this true risk, we're going to just compute the risk with respect to the training data that is available. Okay, so we are going to call that as empirical risk. The empirical risk is simply the loss with respect to the training data. So it's 1 over n, summation over I is equal to 1 to n, the loss in predicting y of I using my hypothesis. Okay, so this risk is known as the empirical risk. Okay, so instead of minimizing the true risk, we almost always try to minimize the empirical risk. Okay, so instead of finding the true H star, we would find H hat, which is R min of the empirical risk. So this whole idea of like approximating the true risk with empirical risk and trying to minimize the empirical risk, right? So this is known as empirical risk minimization. Okay, so now it is very important that we understand that we are doing empirical risk minimization. Why? First note, it's important because there is no guarantee that H star is equal to H hat, right? So like our goal is to find H star. So let me put it here again. So our goal is to find this H star, which is argument of the true risk. On the other hand, like what we end up doing in practice is argument over the empirical risk. So there is no guarantee that H star is equal to H hat. Okay. So for example, let's say this is all possible hypotheses. Okay, and let's say this is H star. It could be the case that H hat is actually far away or like decently like farther than the true H star. Okay, now another note is the inductive bias of the algorithm restricts the hypothesis class. Okay, so even though the true hypothesis class H has all possible hypotheses, the model or the algorithm that you're going to select is going to restrict the type of solutions or the hypothesis. Okay, so let's call the original hypothesis class to be this H. This is the original hypothesis class. Okay, now typically when you use a model, the model will have a restricted hypothesis class, which is a subset of H. Okay, so now what is even worse, this restricted hypothesis class H dash may or may not contain H star. It might be the case that you chose a model like, okay, like a simple example for this is, let's say I have a problem which requires a non-linear decision boundary and I choose a linear model. Okay, now this linear model can only like come up with linear decision boundaries. So my H star on the other hand is going to be some non-linear function, and I would never find that H star by trying to minimize the objective function by using this linear model. So it's very crucial to understand that the model that you're choosing is going to restrict the type of solutions that you're going to obtain. Someone raised hand.
Hi.
Hey.
I have a question about the H hat and H star. Why can we approximate H star with H hat?
No, we are approximating, right? So instead of finding this H star, which is based on the true risk, we are approximating with by using the empirical risk, right? Like so now the problem is this is okay. The reason why H star and H hat could not be same is simply because it's an approximation.
Okay,
Right?
but
If it is,
why this approximation?
it's approximation because you are minimizing only with respect to the data that you have in hand. You don't have access to all possible data points, right? So the true distribution, like having access to true distribution will give you access to all possible data points. On the other hand, like when you work with a data set, it only has, for example, I don't know, 10,000 points, while in reality you could have a million points, right? So it's an approximation of the entire data possible from this distribution.
Okay, all right, thank you.
Okay, sorry. Okay, so now this H dash might or might not have like the true H star, right? So for example, case one is where, let's say we were lucky enough to choose a model which includes H star, right? So in this case, like if this is my hypothesis space, like H hat and H star could be both inside, right? But case two is where, like the example that I gave, let's say H star is non-linear, but I have H hat, which is linear. Okay, so I don't know why my screen has this sharing issue. Just give me 1 second. Okay. Okay, so case two is like H star does not belong to H hat. In this case, like I would be able to find some H hat, but the true H star actually lies outside. I cannot even reach it. Is that clear? Okay, 1 second. Let me also open the chat so that I know. Okay. Okay, so now this is the setup. Okay, so now having introduced the true risk and the empirical risk. So we are going to discuss about one of the central concepts, which is the idea of bias variance decomposition. So we briefly touched about bias and variance in, I don't know, the second lecture or the third lecture, right? Like so when we discussed about k-nearest neighbors versus linear regression, I mentioned that linear regression has very high bias. On the other hand, k-nearest neighbor has very high variance, right? Like so why did I say that? So a lot of people asked this question, like, so what do I mean by bias and variance? So we are going to formally like define what is bias, what is variance, and like so how to compute these entities. Okay, so to do that, we are going to again consider the regression problem. Okay, my loss L of y comma h of x is given by h of x minus y the whole square. Okay, now h star is given by argmin expected value of L of y comma h of x, where h belongs to all possible hypotheses, right? So we have already solved this true like risk minimization problem in the second lecture, and the h star is given by expected value of y given x. Remember, so this is the regression function. Okay, so we know this. So now we are going to consider the loss h of x minus y the whole square. Okay, and I'm going to do a little bit of algebra, like play around with the terminologies here to divide this into two components, divide this loss into two components. Okay, so first I would start with this term, and given that we know e of y given x is the true regression function, like I'm going to add it here by minus e of y given x plus e of y given x minus y the whole square. Okay, so this is the only non-intuitive step. So there are other ways to derive this bias and variance, like, but the way in which we are going to do that is by explicitly adding plus and minus e of y given x. So they cancel out. So the term is the left hand side is still the same as the right hand side. Okay. So now once you have this, now we can do a bit of reformulation here. So I'm going to consider this to be a plus b the whole square. Okay. So it's basically a square plus b square plus 2ab, right? Okay. Now, this is for one particular loss function, right? Like, so now what is the expected value of this loss function? So now that is given by, maybe I would write it in the next page so that it's easy for us to keep it with us while deriving. So the expected value of the loss with respect to y comma h of x is given by expected value of h of x minus y the whole square, right? So now this is equivalent to expected value of these three terms. So let me just copy these terms. Okay. Okay. So now the expected value of these three terms, right? So expected value of the first term plus expected value of the second term plus twice expected value of the third term. Okay. So, okay. So now we took the expected prediction error and we have divided it into three components. So first, we will try to remove the third component. Okay, so first we will show that the third component is 0. Okay, so let's just do that quick derivation. So third component is given by expectation of this whole term, right? So now this expectation is with respect to both x and y. So it's expectation with respect to x, expectation with respect to y given x. So you multiply these things inside. So it's h of x e of y given x minus h of x times y minus expected value of y given x the whole square plus y times expected value of y given x. So all I have done is multiply these two terms individually. Okay, so now let's apply this the first expectation inside. So this becomes expectation with respect to x. So the first term is h of x e of y given x. So the first term is not a function of y, so it just stays as such. The second term becomes h of x e of y given x because you have y there, right? The third term is just a numerical value, so it is expected, it's as such. Okay, and the fourth term, there's a y, so this becomes e of y given x the whole square. Okay, so now look at these terms, they actually cancel each other. So this is basically 0. Okay, so now this, we kind of removed this third term. So all we have is the first two terms. Okay, so let me rewrite that again. So the expected value of the loss is given by expected h of x minus e of y given x the whole square plus expected e of y given x minus y the whole square. Fine. Okay, so now let's call this as the first term, let's call this as the second term. Like we're going to minimize these two terms. So the first term, expected value of h of x minus e of y given x the whole square. Let's expand this expectation. So this becomes integral over x, integral over y given x, h of x minus e of y given x the whole square, p of y given x dy, p of x dx, right? Now, can someone tell me what would be the first integral? So what happens when I integrate this term with respect to y? So you could see that there is no y in this term, right? So this is not a function of y. So simply you remove the expectation. So this becomes integral over x, h of x minus e of y given x the whole square, p of x dx. Okay. Now let's look at the second term. The second term was given by expected value of e of y given x minus y the whole square, right? So now expand the integral. So it's integral over x, integral over y given x, y minus e of y given x the whole square. It's a minus b the whole square. I just made it a b minus a whole square, doesn't matter. So p of y given x dy, p of x dx. Okay, so now what is this integral? Any answers in chat? This is variance. Okay, that's right. So this is the definition of variance, right? So this is variance of y given x. So this is simply integral over x, variance of y given x, p of x dx, right? Okay, so now we did a bit of boring math here, but now let me summarize what we have achieved. Okay, so we started with the expected loss, right? So this is given by, this is given by expectation with respect to h of x minus y, the whole square, right? And we did a bit of algebra, and in the end, we ended up with two terms. The first term is an expectation. So both the terms are actually expectation with respect to x, right? So the first term is expectation with respect to x, h of x minus e of y given x, the whole square, plus the second term is expectation with respect to x, variance of y given x. Okay. Okay. So now you can see that we have this second term. Do you see any h in the second term? No, right? So the second term is just the pure variance of y given x, and it has nothing to do with the model, right? In some sense, the second term is independent of h of x. Okay. Now this is what we call as irreducible minimum value of the loss function. Okay. But look at the first term. The first term is exactly what we would have expected, right? So we know that the true solution for this function is e of y given x. So if I have a hypothesis which is exactly e of y given x, then the first term becomes 0, right? So if h of x is actually equivalent to e of y given x, and we also know that it can never happen simply because we don't have access to the true distribution, right? But if h of x is equal to e of y given x, then the first term goes to 0. Okay. Even when the first term goes to 0, even when you have found the true function that you are interested in, you will not have 0 loss, because there is a second term in the 0 loss, like the second term in the loss, which is the irreducible minimum value, which comes simply because of the stochasticity or intrinsic noise in the data distribution. Is that clear? Okay, so any questions? Okay, so if you did not follow the math, the summary here is we started with the expected prediction error and we divided it into two terms. Okay, so the first term basically says that the first term will go to 0 when you have found the true function, which is e of y given x. But then there is a second term which will never go to 0 simply because it is not in it's not in the control of your hand, right? It's not in your control. It is from the data distribution itself. It's the inherent variance in y given x, which you cannot control. So any questions before we break? Okay, so there's a question. Yumna? Okay, so Remy, can you unmute Yumna? Okay, there is a question in the chat, which is like, what's the difference between h and f function we were talking about? Well, h and f are, h is just a reformulation of f. So every possible, like f is a parameterized model, which has some parameter w, right? So for every possible w, this f of w is the h. It's a hypothesis. Okay, okay, so Yomna, you can ask your question. Okay, you can unmute now.
Yes, I still don't understand, why do we have an irreducible minimum? Where does this value come from? So what do you mean by the noise of the data?
Okay, so if your data distribution itself is stochastic, right? In that case, you're trying to model a probability distribution, and that distribution has its own variance, right? Unless you know the process, you cannot estimate it properly. And like, so we have also seen that even if you know the true distribution, like there is this variance in the generation process itself, which is not controllable, and hence like you will make mistakes. Now even if even if the data or the task is deterministic, we have some noise coming because of the measurement errors that we make, right? So that is another external source of variation. So there are like these variations which are not avoidable, like they introduce noise, and so that is what is captured by the second term. Is that clear? Okay, so what is the difference between finding an optimal hedge and minimizing a regression error? Well, we are interested in finding the optimal hedge star, but we cannot do that. So in some sense, we are approximating it by minimizing your loss with respect to the data set. And that is what we call as hedge hat. Okay, so we will actually take a small break and we will start again at 1:45.